Good afternoon, students. We'll start with lecture 20. Right. In the previous lecture, we have seen we have started with the time response of feedback control system. Just I will brief you out what we have studied. What is time response of the system? The response of the system as a function of time. Right. That is time response of the system. And the time response of the system is divided into two parts. C of t is equal to Ct of t plus Css of t. This we have seen, right? The time response of the system C of t is equal to Ct of t, the transient response of the system plus the steady state response of the system. Right? The system can be either first order system or second order system. That also we have seen. If it is first order system, what is the output we are getting? Right? That we have seen. It was rising exponentially. If I hope this is the unit step input, it was rising exponential like this, right? It was rising exponential like this. So this is time t and this is the response C of t. Right? This is for first order system. If it is second order system, right, this we have seen. Okay, we will be seeing the derivation also. This is unit step input. Then here the damped oscillations, damped sinusoidal oscillations, right? If you remember like this is for second order system, this is for first order system, right? Okay, and if I take the response, it is divided in two parts: the transient response and the steady state response. What is transient response? Right, the variations in the output before achieving the steady state or final value, we call it as transient response, right? And mathematically we can write it as limit t tending to infinity, right? Ct of t, it will be 0 because the transient response vanishes once the system attains the steady state value or final value at time t equal to infinity, right? This we have seen, right? Okay, then what is steady state response? Right, once the transient dies out, it is the steady state response is nothing but the part of the time response of the system once the transient dies out, right? Or else we will say that whenever the system reaches the final value, we call it as steady state, right? Okay, fine. And coming to the standard test signals, the introduction over, then standard test signals. Why these standard test signals are required, right? That such as unit step, step signal, ramp signal, all these are unit step, unit ramp like that, right? Ramp signal, parabolic signal, then impulse, unit impulse. Why we are choosing these four as standard test signals? Because they are representative of the other signals that are existing in the nature, what we can apply for the input. They are representative. Just we'll concentrate only on unit step, will not concentrate on ramp, parabolic and impulse, right? Because for syllabus only unit step response of first order system and second order system it is there, right? Okay, and we have seen if I apply unit step for the whether it is first order or second order system, if I apply unit step input, I will be getting some response, right? Okay, and this unit step will test the system quickness because the signal is changing from one level to another level. If this is the unit step, right? So it is changing from one level to another level at time t equal to 0, right? It will test the system quickness, and also it is representative. If I apply the input signal as the unit step input for any of the system, it is as good as I am testing my system for as good as I am testing my system for sinusoidal signal of various frequencies, wide range of frequencies, right? Instead of applying the sinusoidal signal of wide range of frequencies, I can apply unit step. That is the representative of the sinusoidal signal of wide range of frequencies, right? I hope you understood. Hence we call these signals unit step, unit ramp, unit parabolic, unit impulse as standard test signals, right? Because they are representative of the other signals that are existing in the nature and we are testing the system, right? Okay, then we'll see in today's lecture, we'll see the unit step response of first order system, and if time permits, we'll see also the unit step response of second order underdamped system. What is underdamped? All those things we'll see later. And since there are four standard test signals here, we are considering only, I told, unit step. So the same thing applies here also. Unit ramp response of first order system, unit parabolic response of first order system, unit impulse response of first order system. The derivations are there, but we'll consider only unit step response of first and second order systems. Okay, we'll start with the first thing, the time response of first order system. Already I told what is first order. If I look at the denominator polynomial in the given transfer function, then if the highest power of s is 1, then I will say that it is first order system, right? If the highest power of s is 2, I will say that it is second order system. This thing you know. Okay, we'll start with the derivation. Unit step response of first order system. Okay, we will consider the first order system. It is shown in figure A here, the block diagram of the first order system shown in figure A. You can observe the input is R of S, and output is C of S, and the forward path transfer function is 1 by Ts, and feedback path from output to input, it is unity negative feedback, right? Unity negative feedback. And if I take the transfer function C of S by R of S, this is G and this is H. G is 1 by Ts here, H is minus 1 here. So we know how to eliminate the feedback loop. G divided by 1 plus Gh. We will get the transfer function as 1 by 1 plus Ts or 1 by Ts plus 1. Right? This is the transfer function. So first I will write the transfer function of the given system. Transfer function, that is C of S by R of S, is equal to 1 divided by Ts plus 1 or 1 plus Ts, one and the same, right? Okay. It is 1 and this 1 plus Ts also I can write, no problem. So this is the transfer function of the system. But just look at the heading, unit step response of first order system, means R of S is the input. What should it should be unit step. Whatever the input I am applying, it is unit step input. If I apply unit step input, what is the response of the system that I want to? C of S is the response in Laplace domain, but the response of the system in time domain, because we are analyzing in terms of time domain. Frequency domain we'll see it later. So time response of first order system, right? So C of S, I will get some equation, right? Take inverse Laplace transform, I will be getting C of t. I want the response, right, in terms of time domain. So that is C of t. Okay, C of S is there. Then what is R of S? That is unit step, right? So for unit step signal, what is R of S? 1 by S, if you remember, right? Yesterday I told for, okay, I have summary I have done for unit step, ramp, right? Then parabolic, then impulse. So it is Laplace domain. Yesterday I told you. So 1 by S, 1 by S square. So 1 by S cube. I hope you remember, right? So all these things, and it is 1 for impulse, right? So if the input is unit step, so R of t is 1. Then if it is in Laplace domain, it is 1 by S, right? R of t is 1. So unit step is signal. So R of S is 1 by S. So I'll substitute R of S. I'll send R of S that side. So what is C of S? I'll write C of S is equal to, take this R of S this side. What is R of S? It is 1 by S. So 1 by 1 plus Ts, or else I will take 1 by S here, right? Because R of S into this remaining thing, right? This is R of S. So C of S is equal to 1 by S into 1 plus Ts. So okay, let me rearrange it, because I should be knowing the partial fraction expansion, and I have to take inverse Laplace. Directly I cannot take. First I have to rearrange in the standard form. Okay, let me take T as common. First I will take this term. T has been taken. S plus, right? First I am taking this. T is taken common. S plus 1 by T. I hope you agree with me, right? So C of S is equal to, okay, let me remove this. I will write it here. 1 by S into this T, I will take it to the numerator, 1 by T divided by S plus 1 by T. Okay, then I will expand it using the partial fraction expansion. So there is one standard formula. I will show you here in the next slide. It is there. Suppose the term is factor is like this, k divided by x plus a into x plus b. This is the factor. Then in the partial fraction expansion, this is the standard form. I will get k divided by b minus a into 1 by x plus a minus 1 by x plus b. This is the what I am going to use here, right? Okay, I will make use of that. Observe here, k is, I'll write it 1 by t into s plus 1 by t. So k divided by x plus a into x plus b, right? So k divided by x plus a is 0 here because s plus 0, right? A is 0 here. X plus b, x means s here, x plus a into x plus b, right? So a is 0, b is 1 by t. So let me write it here, a is 0, b is 1 by t, and k is 1 by t. B is also 1 by t, and k, this is k, right? So I will make use of the k divided by b minus a. K divided by b minus a, 1 by t minus 0, it is 1 by t only, into, observe the formula, 1 by x plus a minus 1 by x plus b. 1 by x plus a, x plus a, x means s here, s plus a, what is a here? 0, s plus 0 minus 1 by s plus b, sorry, x plus b. X is nothing but s, s plus 1 by t. So 1 by t will get cancelled. So C of S is equal to so I will write 1 by S minus 1 by S plus 1 by t. Okay, then I want the unit step response of first order system. This is C of S. So take inverse Laplace transform, right? So take inverse Laplace transform of above equation, this one. So we should be knowing what is the Laplace transform, right? So C of t is equal to, so inverse Laplace transform of 1 by S is 1 minus inverse Laplace transform of 1 by S plus t means we know that Laplace transform of e power minus at is equal to 1 divided by S plus a. Is it fine? So 1 by S plus a, this is right, e power. So inverse Laplace transform of this is e power minus at. Inverse Laplace transform of 1 by S plus a is e power minus at, right? So e power minus a is this one, right? So minus at minus t by 1 by this one, right? I hope you are getting at minus at. This t, a is 1 by t. A is 1 by t. I hope you are getting this. So this is the unit step response of the first order system. This is the unit step response, right? And we can plot this. What is the unit step response curve we are going to get for different values of t, small t. T can be 0, t can be t. This capital T is time constant. So t can be t, 2t, 3t. I can just go on calculating for various values of t, right? And I can plot the curve. That I will call it as unit step response curve, right? So this is the unit step response of the first order system. That is C of t is equal to 1 minus e to the power of minus small t. This is small t. T by t. This capital T is time constant of the system. I will tell you what is this time constant, right? And one more thing, this is, I told this is first order system, right? Because look at the denominator here, the s power of s is 1 here, right, in the transfer function. So hence this is the first order system. Yesterday I was, while discussing, I told you first order system, it may represent simple RC circuit also. It may represent some thermal system also. If it is RC system, we got the transfer function. Already we have seen in the previous chapter. C of s by R of s is equal to 1 divided by 1 plus SRC. You can compare with this. 1 divided by 1 plus SRC means T is RC. T is RC here, time constant, right? It depends on the values of R and C, the time constant. If it is RC circuit. If it is thermal system, the parameters may vary. Time constant depends on some other parameters, right? I hope you understood. Okay, this is how we have derived the unit step response of first order system. Next, we have to draw the curve, right? Unit step response curve of the first order system. Okay, okay, this slide I have written the formulas for reference, right? So okay, next. So already we know that this is the unit step response of the system. 1 minus e to the power of minus, I have written here like this, C of t is equal to 1 minus e to the power of minus t by t, right? Like this, they have written like this, right? T by t for t greater than or equal to 0. Is it fine? This is the unit step, already we have obtained. Then for various values of t, yes, substitute t equal to 0 here, right? If this is 0, what will happen? This term will be 1. 1 minus 1, 0. So locate it here. And x-axis is time axis t, and y-axis is C of t, the response of the system. Y-axis, the response of the system. For various values of t, just go on plotting the values. Then for t equal to 0, we got the point as 0. Then for t equal to t, substitute, right? For t equal to 0, C of t is what? C of t we got it 0, because this will be 1. 1 minus 1 will be 0. Then for t equal to t, substitute. So substitute t equal to t, e to the power of minus 1. Calculate in your calci 1 minus e to the power of minus 1. You will get this value for t equal to t. That is C of t is equal to 0.632. You will get it. 0.632. In terms of percentage, it is 63.2%. So represent it here, 0.632. I told you this one, right? So this is the unit step signal. Observe here, this is our reference because we are applying the unit step signal as input. So this is our unit step signal. Just observe here, this is our unit step signal, right? With respect to this unit step signal, the response of the system we are plotting, right? So for t equal to 0, the C of t is 0. For t equal to t, the C of t is 0.632. Yes, in terms of percentage, 63.2. For t equal to 2t, calculate C of t, it turns out to be 0.865. 0.865. Plot it. So 0.865 somewhere corresponding to 0.865 here. 0.865 corresponding to this. Right? Somewhere. Next, in terms of percentage, it is 6.5%. So for t equal to 3t, you can make use of calculator and calculate. You will get the same values. Right? So t equal to 3t, you are getting 95%. 95% is 0.95. So 0.95. Right? 0.95 corresponding to this 0.95. So 95%. Then for t equal to 4t, C of t you calculate. So it is 0.982 you are getting. So 98.2% in terms of percentage. So 0.982 just corresponding, right? 0.982. So for similarly for t equal to 5t, we can just go on finding out. So we'll stop here. C of t is equal to 99.3% I will get, means 0.993. So here 0.993 here somewhere, right? So it is 0.993 and okay, 1 minute. Yes. So in terms of percentage, 99.3%. I hope you are getting right. And you can observe one thing, for t greater than or equal to 40, means at this value for t greater than or equal to 40, the percentage means the output or the response of the system lies within plus or minus 2%, right? Plus or minus, the output or response lies within, the response lies within 2%, right? For t equal to 40, you are getting 98.2, means for 100 it is just 2%, means the tolerance or response will be within 2%, right? So for t equal to 5t, you are getting 99.9, means for t greater than or equal to 40, the response lies within 2% of the reference. Reference is our, this is the reference unit step signal, right? So if I treat 1 as 100%, this is 1, right? In terms of percentage is 100%. If t is greater than or equal to 40, the response will be within 2% of the final value, right? Okay, I hope you understood. Then okay, connect all these dots, you will be getting the response. Connecting all these dots here like this, connect all the dots. It is nothing but rising exponential, right? Rising exponential. Connect all these dots, and at time t equal to infinity, it will reach the desired value or steady state value. At time t equal to infinity, as time progresses to infinity, the system will attain the steady state value or final value. Final value is, this is 100%, this is my reference unit step signal, right? At time t equal to infinity, the system attains the steady state, right? I hope you understood. Then how to find out the slope at time t equal to 0, right? The time t is 0 here. What is the slope of this line? I want to find out. So 0 to t, just take this line, right? Here it is there. How to calculate the slope of the line, we'll see. Take the derivative of the response, d by dt of c. C means c of t here, this one, c of t. Take the derivative of c of t with respect to time t, means d by dt of c of t at time t equal to 0, so that it will give me the slope. How to find out the slope? The slope of the curve at time t equal to 0 is given by d by dt of c of t at time t equal to 0. So take derivative of 1 is 0. Then derivative of minus is there, minus derivative of e to the power of minus t by t. It is 1 by t into e to the power of minus t by t. This minus and that minus, minus into minus, it will become plus. So I will be getting 1 by t into e to the power of minus t by t. I hope you are getting. Take derivative of c of t. C of t is here. Derivative of 1 is 0. Minus derivative of e to the power of minus at. Right? I hope you are getting. So minus a. Right? Minus to minus, it will be plus. So minus 1 by t, minus into minus, so plus 1 by t e to the power of minus at, minus t by t. And substitute t equal to 0 here, small t. If this is 0, means this entire term will be 1. E to the power of minus 0 means anything to the power of 0 will be 1. So this is 1. So finally I will be getting the slope as 1 by t. So this slope, this line, just draw this line, observe here. Right? The slope of this line is 1 by t. How to find out the initial slope? The initial slope at time t equal to 0 is 1 by t. Then what is the slope at time t equal to infinity? This is at time t equal to 0. At time t equal to infinity, what is the slope? Can you anyone tell? Observe here. At time t equal to infinity, the system will attain the final value or steady state value. So the slope will, what is the slope will be 0. Slope has to be 0. right? So at time t equal to infinity, slope is 0. Slope is equal to 0. But initial slope is 1 by t. It depends on the time constant. But at time t equal to infinity, so you can observe here the desired value or the steady state value and the response that has been achieved both are parallel to each other. Hence slope is 0. The line will be parallel like this. So hence slope is 0. I hope you are getting right this thing. Okay, this curve we call it as unit step response curve of the first order system, right? Okay, then something I have to tell about this capital T means time constant. Okay, we'll see in the next slide. Yes, the time constant. What is this T in this response of the system? This capital T time constant will tell us. The time constant, it is indicative of how fast the system tends to reach the final value. Here in this graph and this graph both are one and the same. But here we have plotted this graph for two different time constants, T1 and T2. T1 and T2, two different time constants. Okay, if I plot for time constant T1 for T equal to T1 here, this is the plot for T equal to T1. This is the plot. Okay, and it will attain the final step. Let me change the ink color. Let me take some other ink. Okay, let me take blue color or else some other color. Okay, let it. Yellow, let me take yellow. Okay, okay, it's not visible. For T equal to T2, for T equal to T2, so this is the graph, green color. What is the difference I am getting? I'll tell you. Just I will draw it first, then I'll show you. So with different colors means you will. So this is for T equal to T2. This is for red color T equal to T1. But observe here T2 is less than time constant T2 is less than T1. Means the time constant T1 is more as compared to T2. So if the time constant is less, the system is here. You can observe here the system responds very fast and it will try to achieve the final value at the earliest. If time constant is large, that is t equal to t1, the system slowly rises and it will achieve the steady state later, right? But the response of the system is slower whenever the time constant is large at time t equal to t1, but the system will be fast whenever the time constant is less, right? I hope you have understood this. You can observe here. One more thing I will tell you how it is fast, how it is slow. I will show you. For example, the time constant, right? It is indicative of how fast the system tends to reach the final value. Let me assume that at this instant, let me take this is 100%. Let me take x% of final value. Let me assume this is 50% or 60%, something like that. In order to achieve 50% of the final value, just whenever time constant is t equal to t1 and whenever time constant t equal to t2, what is the time it is going to take? I will tell you. See here, in order to achieve 50% of the final value, just take this dotted line. Now let it intersect both the curves for t equal to t2 and t equal to t1. Corresponding, read the values of the time here. It is ts1 and ts2. In order to achieve 50% or x% of the final value, the system having smaller time constant will take less amount of time. The system having the larger time constant will take more amount of time. Means the system is very much faster whenever the time constant is less, t2 is less than t1, right? So the system with large constant I have written here, the system with larger time constant will give corresponds to a, it is a very slow response or sluggish system, or the response is slow response or sluggish system also we say. And system having smaller time constant corresponds to faster response. Here it is slower response, here it is faster response, right? System with larger time constant will be having slower response and the system having the smaller time constant will be having the faster response. I hope it is visible here and I have shown you here also. It is proved here, right, at these values. I hope it is clear. If anything, any doubts are there, please unmute yourself and talk to me so that I can clarify your doubts immediately, right? Okay.
Excuse me, sir.
Yes, tell me. Yes, sir, Prem Sai.
Is it like both the systems will reach 100% at the same time, sir?
No, we don't know because at time t equal to infinity, it will reach infinite, steady state or final value. At time t equal to infinity.
Okay, sir.
At time t equal to infinity. Yes. Okay, fine. Next, the speed of response. What is speed of response, right? Just we will define this thing. It is quantitatively defined as the time for the output to become particular percentage of its final value. I told in order to achieve 50% of the final value, you have taken the readings, right? This is the speed of response. The speed of response is good in case of the system with smaller time constant. The speed of response is very slow, right? The speed of response is very slow for the case with the larger time constants. I hope you are getting what I am telling, right? Okay, next. So this is the unit step response of the curve for two different time constant. This is the unit step response of the curve for various values of t equal to 0, t equal to t, t equal to 2t and 3t and so on, right? For this capital T is nothing but time constant. For different time constant, this is the unit step response curve for different time constants. One time constant with a smaller time constant and another with larger time constant, right? Two for two different. For three also I can take. Just go on, but for example, we have taken only two, right? The next, whether system has any error or not, we have to find out, right? You can observe here, I will come to this. So R of S, and this is the feedback signal C of S is coming here, and here it is error signal E of S, right? In terms of time domain, E of T I will write, right? So this is in terms of time domain, it is E of T, and this is R of T, and here CS, unity negative feedback is there. So in terms of time domain, I will write E of T is equal to, right? Right, R of T, I am writing this is R of T in time domain minus C of T. In Laplace domain, E of S is equal to R of S minus C of S, because it is unity negative feedback. Whatever the signal that is coming is feedback signal is CS here. So minus CS. I hope you are getting. So in terms of Laplace domain, ES is equal to R of S minus C of S. In time domain, E of T is equal to R of T minus C of T. So we will assume, we will see whether is there any error. Okay. Yesterday while telling steady state error, if the system reaches the final value or steady state value, then there is no error. Let us see, is there any error for the first order system, unit step response of first order system. We will see. Yes, the error response of the first order system is given by E of T is equal to R of T minus C of T. Just now I told, right? So what is R of T? So let me rewrite here. E of T is equal to, here I have written R of T minus C of T. What is R of T? It is unit step input, right? Whatever the input I am applying is unit step. Unit step input, right? So it is R of T is equal to what? U of T, that is equal to 1. Yes, unit step input, right? 1 minute. Let me go here. So unit step, it is 1. So R of T. R of T is nothing but 1 minus open bracket. What is C of T? You have found out the response. C of T is 1 minus e to the power of minus t by t. So 1 minus e to the power of minus t by t. So 1 you will get cancelled. What I'm left out, I have written here E of T is equal to e to the power of minus t by t. I hope you are getting how you got it, right? So E of T, the error response is e to the power of minus t by t. But what is steady state error, we have to find out. So the steady state error is given by, so ESS of t, ESS of t with function of, with respect to time only, ESS of t is equal to limit t tending to infinity E of T, sorry, E of T. What is E of T? E of T here is e to the power of minus t by t, right? So e to the power of minus t by capital T at time t equal to infinity. So substitute here infinity. So e to the power of minus infinity, 1 by e to the power of infinity, 1 by infinity, 1 by infinity is 0. So what is the steady state error for first order system? It is 0. Means the system will achieve the steady state value or final value at time t equal to infinity, right? T equal to infinity. I hope you understood, right? Means there is no steady state error in the first order system, because the system is going to attain the steady state value at time t equal to infinity, right? Okay, then what is the meaning of this? If steady state error, this means that the first order system tracks the unit step input with 0 steady state error, because you take whether the system time constant is less or small. Finally at time t equal to infinity, they will reach the steady state value here like this, because it is tracking this unit step input, right? See, if the time constant is less also, it is achieving the final steady state value at time t equal to infinity. I hope you are getting, right? So there is no steady state error in case of first order system whenever it is subjected to unit step input. I hope you came to know. If any doubts, please let me know it. Okay, similarly, okay, let me change the ink. Similarly, we can find out just now we'll take the same system. Instead of unit step, apply unit ramp. Instead of unit step, apply unit ramp, apply unit parabolic, unit impulse, and get C of S or C of T. How we have obtained here? C of T we have obtained here, right? Similarly, but with the derivation is not there for you people. So just I am giving. So similarly, we can find out unit ramp response of the first order system. Similarly, we can find out unit impulse response of the system, but we will not see the derivation. Just we will have a look at the formula. First one, unit ramp response of first order system. If the input for the first order system, this suppose let me assume that this is the first order system. So this is the input R of S and output is C of S. So here the input is instead of unit step, here we are applying unit ramp signal, right? And we are getting some response C of S. Take inverse Laplace transform, we will be getting C of T like this one, C of T. C of T is equal to T small t minus this time constant, capital T is time constant, minus T plus T into e to the power of minus T by T. So take T common, they have written for T greater than, this is the unit ramp response of first order system, this one, right? This equation, only this much, right? This is the unit ramp response of first order system. Then what is steady state error? Okay, let me see here. ESS, limit t tending to infinity e power t. What is e power t? You know, e power t is r of t minus c of t. R of t is the unit ramp, so you subtract it and apply t equal to infinity, you will get t. Means we can observe here there is a error. There is a error. Steady state error is, it depends on the time constant t. You observe here this x-axis is time and this y-axis is r of t. Sorry, actually c of t. The response c of t. Then the unit ramp signal, this is the input, unit ramp signal, this is the input. Then this equation C of t is equal to t minus t for t equal to 0, comma for t equal to t 2t, just go on plotting, you will get this curve. Just I'll change the ink to, yes, this is the response what we are getting. It goes on, right? We can observe this is the desired output, this is the actual output. So this steady state error is here, the steady state error, that is t, ess of t is equal to t. This is what we have found out here, right? So the unit ramp response of first order system has steady state error that is equal to time constant, depends on time constant t, right? And you can see one thing, that the system will never attain the steady state here. The system will never attain the steady state, right? It goes on, it will never attain that, because there is a error, there is a difference between the desired output and the actual output. This is the desired output and this is the actual output. So derivation is not there. Just I will to compare, if the, if instead of unit step, if I apply unit ramp, what will happen? Instead, then if I apply unit impulse, what will happen? Just we'll see and we'll compare for the linear time invariant systems later, right? Okay, I hope you understood this. The next, unit impulse response of first order system. Instead of this unit ramp, we'll apply unit impulse here. Unit impulse for the first order system, right? So what is C of t? So after derivation we got it. C of t is, derivation is not there. C of t is equal to 1 by t e to the power of minus t by t. It is decaying exponential, you can see here. It is decaying exponential. Time axis, and this is response C of t, right? For t greater than 0. Yes. The next steady state error we are not calculating here. Just you should be knowing how it should look like, right? Next, with respect to all the responses we have seen, the next we'll compare. There is an important property of LTI system, linear time invariant system. If the system is time varying and if the system is non-linear, then this property does not hold good, whatever we are discussing right now, right? It is applicable only for linear time invariant systems. Okay, just now we have seen unit ramp response of first order system. This equation we know, C of t is equal to t minus t, but we have not derived. Just I have shown you t minus t plus t into e to the power of minus t by t for t greater than or equal to 0. Then unit step response, it is 1 minus it, this we have derived, this we have done. Right, okay, just we have listed the responses here. For unit impulse, I will be getting this decayed exponential. C of t is equal to 1 by t e to the power of minus t by t. And whatever I have written, this is important here, right? So if I want to find out unit step response of first order system, it is nothing but derivative of unit ramp input. So this is the response of if I apply unit ramp as a signal, this is the response. Take the derivative of it, I will be getting the unit step response of first order system. Take the derivative. So with respect to this is 1, right? So this is 0 with respect to t, d by dt of c of t, right? D by dt. So dt by dt it is 1. This is constant, so it is 0. Then this one, derivative of this. So you take this minus sign will come here, e to the power of minus t by t. This t into 1 by t, they will get cancelled. So I will be getting e to the power of minus t by t. So I can say that the derivative of unit ramp input is nothing but the unit step response of the first order system. In other way, I will say that, right, derivative of unit ramp is unit step response of the first order system, but integration of unit step response is nothing but the response of the unit ramp input. The integration of this will give me this, integrate this, you will get this, right? The integration of unit step response is nothing but the unit ramp response of the first order system, other way around. Just observe here next. Unit impulse response of the first order. It is nothing but the derivative of the unit step input. So the response is here. Take the derivative of this. Derivative of 1 is 0. So take minus, the sign is there. Derivative of e to the power of minus t by t with respect to time t, small t. So I will be getting minus into minus plus 1 by t e to the power of minus t by t, right? So the derivative of unit step input is nothing but the unit impulse response to the first order system. Or in other way around, the integration of the unit impulse response is nothing but the response of the unit step input, other way around. I hope you are getting, right? So there is interrelation or correlation, and this is one of the important property of linear time invariant system, but this property we are not going to use anywhere, but we should be knowing it, right? So only thing what we have studied is only this unit step response of first order system. Only this is sufficient for us, but we are comparing with respect to unit ramp response and unit impulse response, right? How they are related, whether taking derivative of this will give me the unit step response, all those things we should be knowing. Then next we'll proceed with the second order systems, right? uh, okay, in 20 minutes I can finish or not. Okay, let me check it. Second order systems. Okay, before starting with the derivation of the unit step response of second order, we have done the derivation of unit step response of first order system. So similarly, there is derivation of unit step response for second order system, right? Okay, before seeing that, I should understand something, right? So this is the unit step response curve of first order system, unit step response curve of first order system. Then similarly, if I look at the unit step response curve of second order system, we have not yet seen. So it will be damped oscillations like this. It will increase and oscillations are going to die out, right, at time t equal to infinity. Damped oscillations. So this is the unit step response curve of the first order system. This we have seen already. Then this is the unit step response of the second order system. This figure B, right? Okay, just we'll see this point. Every practical system takes finite time to reach its steady state, and during this period it oscillates or increases exponentially, because we are studying only first order system and second order system, not third order, fourth order, and so on. Because the second order system itself is the representative of the higher order systems. If I go for higher order systems, the feedback loop, in the feedback loop, the number of integrations will be more and it will lead to the complexity. So we'll stop at second order system only, right? Okay, I will say that every practical system takes some finite time to reach its steady state. Means steady state means time. In the first order system, we have seen that at time t equal to infinity to achieve the steady state. This we have seen, right? The steady state error is 0. But here the error, there is a error shown in this diagram. But at time t equal to infinity, it will be 0 in case of first order system, that we have seen, right? So either it oscillates or increases exponentially. It oscillates in the case of second order system, right, for unit step input. Then it increases exponentially in case of first order system for unit step input, right? Before achieving the steady state, there is a transient response. This here it is attaining before this. This is transient response and this is steady state response, right? From here to here, transient, because the variations in the output before attaining the steady state. Here also same thing, ct of t, css of t, right? The variations are constant here, still the variations are here. So the variations in the output before achieving the steady state, we call it as transient response, and steady state we have defined it already. The next, behavior of the system. how we can decide the behavior of the system. We'll see. The behavior of the system can be decided by the type of the closed loop poles and the location of the closed loop poles in the S plane. Yes, you know that. Just I will show you roughly the diagram. S plane is a complex plane, right? S plane. This is the S plane, and it is a complex plane. Sigma is the real axis. J omega is the imaginary axis. And I can divide this S plane into two parts, left half of S plane and right half of S plane. Let me change the ink. Okay, let me change the ink color. Left half of S plane with red color I will draw here. This is the poles which are lying on the left half of S plane, and I will change the another color. Right half of S plane like this. Right? Okay. Okay, if the poles means if I have the transfer function, it has both numerator as well as denominator, right? This is the transfer function. Closed loop transfer function, it has numerator as well as denominator. And the closed loop poles means the denominator, if I equate it to 0, if I equate the denominator to 0 and calculate the roots, those are nothing but our closed loop poles, right? So those closed loop poles are nothing but roots of the characteristic equation. Characteristic equation means the polynomial in the denominator. If it is equated to 0, that equation we call it as characteristic equation. In the roots of the characteristic equation, we call it as closed loop poles. And the roots are having location in the S plane. If the roots are located in the left half of the S plane, the system is stable. The system is stable. If the roots are located on the right half of the S plane, the system is unstable. If the roots are located on the imaginary axis, it is marginally stable or conditionally stable. Marginally stable or conditionally stable. There are three. If the roots are located on left half of the S plane, the system is stable. If the roots are located on the right half of the S plane, the system is unstable. If the roots are located on the imaginary axis, the system is marginally stable or conditionally stable. These things. Based on the location of the roots or closed loop poles, we can judge the behavior of the system, whether it is stable or unstable or marginally stable. This you have to understand thoroughly. I hope, right? But here, based on the location of the poles, we will see it later. Okay. Then the closed loop poles are dependent on the selection of the parameters of the system. So for second order system, which are the parameters we'll see, and how the location of the poles will vary, whether they are lying in left half of S plane or right half of S plane or an imaginary axis, we'll see it later, right? Okay. If I start deriving, this will not be over, so I'll stop my lecture here because still 15 minutes is there, but I cannot continue with the derivation, so I'll stop here only. 1 minute. Before stopping, I want to tell you a few more things. And what is stable system? What is unstable system? Can anyone tell? Already I have defined what is stable system. The systems, yes, I will define, please listen. The systems in which the system which is going to attain the steady state value or final value, such systems are called as stable system, right? So here the first order system, unit step response of first order system, we have seen, right? It is going to attain the steady state value or final value at time t equal to, so this is stable system. And once again, if I take the unit step response, this we have not seen, but looking at the curve response, I can say the oscillations are dying out, right? You can see here the oscillations are dying out at time t equal to infinity, so it will attain the steady state. So it is also stable system, right? Okay. Suppose the oscillations are like this. Observe here. This is t, then this is c of t, 0, right? If it just observe here, this is the unit step input, this is unit step input with respect to this. If this is the response what I am getting, observe here. I hope you are getting. So it is rising. These are rising oscillations. These are damped oscillations. So the system is never going to attain the steady state value or final value. Hence, these systems will come under unstable category. These are unstable systems. These two are stable systems because at time t equal to infinity, they are going to achieve the final value or steady state value. Right? I'll stop recording here only. With these all things will be discussed tomorrow.